Okay, so in question 28, what we have here is we have the situation of a spring hanging from a ceiling, and this spring is of course vertical. And hanging off the end of this spring is a block of mass M1. And we're actually told what the mass of this thing is. The mass of that block is equal to 3.2 kilograms. So what is happening here is this block is just hanging there stationary. So the gravity force on this block is being exactly balanced out by a spring force acting upwards. And so in order for this spring to apply such a force, it has to be stretched away from its natural length. And I'll call the amount of stretching x1. And something else we're told about this is that the amount of elastic potential energy which is stored in this spring block system is given by, or actually rather is, 1.8 joules. So that's what the situation looks like to start with. But then what happens is that someone comes along, takes this 3.2 kilogram block away, and replaces it with a 5 kilogram block instead. And then it's allowed to hang stationary. And so that means that the spring is going to have to apply a bigger force to this block to prevent it from falling under its own weight. And so it's going to stretch by a bit more. So I'll call the 5 kilo block, I'll say it has a mass of M2, and the amount by which the spring is stretched, in the case of M2 being attached to it, I should call X2. And what the question is asking us is, what is the elastic potential energy stored in the spring block system in this case here? So again, we're told that what the mass of the block is. It's 5 kilograms. And the question wants to know, what is the elastic potential energy stored in this case? So we have to figure this out. Now, to figure that out, what we're going to have to know is, first of all, we're going to have to know the amount by which this spring is stretched. The other thing, of course, we need to know is the spring constant of this spring, because elastic potential energy is given by a half times the spring constant times the amount by which the spring is stretched squared. And unfortunately, we don't know what the spring constant is, and we don't know by how much the spring gets stretched in the second of these, in this case here. But hopefully, from the information they've given us for the case of block 1, we can figure out what the spring constant is. And hopefully, if we can figure out what that is, we can then figure out the amount by which this spring is stretched in the case of the 5 kilos being attached to the end of it, which will then allow us to get what the elastic potential energy is. So first of all, for the case of block 1, so let's consider block 1. In this case, we know what the elastic potential energy stored in the spring is, and we also have a formula for that in terms of the spring constant and this x1. So that is given by a half times k times x1 squared, where k is the spring constant. And so we know this, but we don't know k and we don't know x1. So we've got one equation with two unknowns in it, so we need another equation before we can solve for either of these two. Something else we can note, however, is that because this block is just dangling there stationary, that means that the net force acting on it is just 0. So whatever force this spring is applying to the block, it has to be exactly balancing out gravity. So let's just write up a coordinate system here. And we can say that since block 1 is stationary, the net force on it is just 0. And so that means that the net force in the y direction has to be 0, and we know that the net force in the x direction is 0 because there just are no forces in the x direction. The only forces acting on this block are gravity and the spring force. So we can then say that the net force in the y direction is going to be equal to the y component of the gravity force plus the y component of the spring force, and they have to sum up to 0. Now we also know then, because we know the mass of this block, we know what the magnitude of the gravitational force is. This is going to be the mass of block 1, so that 3.2 kilograms times by g. And since the gravity force is acting straight down, we need to put a little minus sign there. And the spring force is acting straight up, so its y component is going to be positive. And it's going to be given by the spring constant multiplied by the amount by which the spring is stretched. And all that has got to be equal to 0. Now what we see here is that we could do something quite useful with this equation. If we could solve this equation here for, say, x1 in terms of k, what we could then do is to plug, or perhaps even k in terms of x1, we could then plug that result back into this equation here for the potential energy, and then, having eliminated one of k or x1, we would then have one equation in only one unknown, which we could then solve. So the one that I think would be particularly good to get rid of here is probably x1, because what we're really interested in is the spring constant. Because once we have that spring constant, we can then use it up here and hopefully figure out the amount by which this spring is stretched and then get the elastic potential energy stored in this system. So let's solve this equation here for x1 in terms of k. So we can say solve for x1. So to solve for x1, let's add m1g to both sides of this equation. So we're going to have, doing that, we get that k times x1 is going to be m1 times g. And then if we just divide both sides by the spring constant, we get that x1 is m1g divided by k. And now what we'd like to do is to plug it into here. So we can say plug x1 into formula for the elastic potential energy. And so we get that US1 will be equal to 1/2 times K times by M1G divided by K all squared. And now this thing here, this all squared bit, is just going to be M1 squared times G squared divided by the spring constant squared. So here we have the spring constant divided by the spring constant squared. So this is just going to be equal to 2 times K. And this K is the thing that we want to solve for. So to solve this equation here for K, what we can do is multiply both sides of this equation by K. So if we multiply both sides of the equation by K, we then get that US1 times K is going to be 1/2, because M1 squared times G squared divided by 2 is just the same as multiplying these two things by 1/2. And we get that. And so finally, we're able to solve for the spring constant, which is going to be M1 squared G squared divided by twice the elastic potential energy. So we now know what the spring constant is. So we know one of the unknowns in the elastic potential energy formula for the case of block 2, which is the 5 kilo one. The only other thing we need to figure out is what is the distance by which this spring has been stretched just to hold up the 5 kilo block. Equation star, we can just say, since block 2 is stationary, we have this by analogy with equation star. And so now, since we know what the spring constant is, we can calculate this x2, which we can then plug into there. So we can say finally, hence, EPE in spring block system is US2, which is equal to a half times K, which is this monster over here, M1 squared times G squared divided by 2 US1, and then multiplied by x2 squared, which is this thing. So we're going to have M2 G divided by K squared. So in fact that was silly because I could have just cancelled out K's. So let me just go back a step. This is going to be K M2 squared G squared divided by K squared, which is a half M2 squared G squared divided by K. And so now we have a divide by K, and so we're going to have that this is a half M2 squared G squared divided by all this rubbish, which is M1 squared G squared divided by 2US1. Now here we have a fraction in the denominator for another fraction. So effectively we have something divided by a fraction. Now when you have something divided by a fraction, it's just the same as that something multiplied by the fraction, but with that fraction flipped upside down. So this is equal to a half M2 squared G squared 2US1 divided by M1 squared G squared. So there's a few things which cancel out here. First of all, these G's go away, and now we have a half multiplied by 2, so that goes away. So what we're finally left with is that the elastic potential energy stored in the spring block system in the case of the 5 kilo block being attached to the end is just the elastic potential energy stored in the case of the 3.2 kilogram block times by the 5 kilo mass squared divided by the 3.2 kilogram mass squared. So it comes out to be as simple as that. 7.8 joules.